Hello and welcome to my Physics 2212 lab number 4. So today we're going to discover the behavior of the flow of charge in an electric circuit. So the biggest model that we need to talk about today is the model for the flow of electric charge. So the flow of electric charge through a closed circuit of conductive material is directly dependent on the electric potential and inversely dependent on the resistance within that circuit. So the main results of this lab were that when a circuit including a battery, capacitor, and light bulb were hooked together, the current flowed for about 1 minute and 13.69 seconds. When a capacitor was attached in its own circuit without the battery, the discharge time until the light bulb extinguished was now 1 minute 2.7 seconds. Ultimately, electric potential in a circuit follows the principles of current in a wire. So the main physics idea we need to take that's derived off of the basic current flow idea are the Kirchhoff's laws. So Kirchhoff's laws are qualitative statements describing the behaviors of electric charge flow in a circuit. The loop rule states that in a circuit with a number of resistors wired in parallel, resistance will add linearly, while the junction rule states that the electric current flowing in all wires into a junction needs to equal to the current flowing out of that junction. So to begin the experiment, first a circuit is constructed with two 1.5 volt batteries, a 47 and 100 ohm resistor, and an ammeter all in series. The circuit is measured using the ammeter to determine the current flow in that circuit, in that situation. Next, a circuit is constructed using two 1.5 volt batteries, a 30 ohm light bulb, and a 200 millifarad capacitor all in series. The current was allowed to flow through this circuit until enough charge was moved to prevent flow through the capacitor, extinguishing the light bulb. Finally, the capacitor was discharged through the light bulb in a separate circuit. Behavior of each circuit was detected through an ammeter or through a timer in the latter two and used to establish the behavior of charge flow. For all experiments, the system includes the wire, circuit components, and the ammeter in the experiment in which it's attached. The surroundings are the rest of the universe. So the initial conditions for this lab are as follows. In the first test, a light bulb is attached to a circuit including a 47 and 100 ohm resistor, an ammeter, and two 1.5 volt batteries in series. That is the circuit on the left. The second sees two 1.5 volt batteries, a 30 ohm resistance light bulb, and a discharged 200 millifarad capacitor being connected together. That is the circuit on the right. In the third, the now charged capacitor is finally connected to a light bulb. That's the circuit in the middle. So the assumptions that were made for this lab were that the capabilities of each electronic component were as advertised, i.e. the batteries put out 1.5 volts, resistors had the assumed resistance values, and so on and so forth. The capacitor is also fully discharged during the second two tests. So for the first experiment, the measured amperage was 0.01 amps. The calculated value using the technique demonstrated earlier was 0.02 amps. So for the second experiment, the time to fully charge a capacitor, which is detected from the time the circuit was all connected to the time that the light bulb completely went out, was 1 minute, 13.69 seconds. In the third experiment, the capacitor was discharged in 1 minute, 2.7 seconds through the light bulb. So to discuss these results, Kirchhoff's loop rule is a relatively good approximation of the behavior of an electric circuit. While small differences in the measured and predicted amperage from the first test don't fully match what was measured, the numbers are close enough and the error is in a reasonable direction. The increased internal resistance from the battery likely increased the charge time compared to the discharge time of the capacitor light system. So while the circuits are simulated, considered as having resistance sources only at the distinct electronic components that specifically caused extra resistance, every single component in an electric circuit has a resistance, including the batteries and the wires. Therefore, in the trials where the batteries were removed or less wires are used, less resistance will be encountered than expected. So to answer the what if, what does it mean questions, while we did use a real ammeter for this lab, it likely definitely contributed some extra internal resistance, like all other electronic components. This further reduced the amperage that was measured in the first circuit. In addition, in the situation of when we consider the effects of using a real capacitor being charged off of a real battery, a real capacitor should charge slower when charged from a real battery in circuit. This is a result of the internal resistance of the battery and the wires, which reduce current flow, which in turn reduce the rate of the capacitor receiving charge. So with all of that said, that should be everything for this lab. Thank you very much for watching, and see you guys in 2 weeks.